Recording in progress.
Okay, we will start now. I share one notes here. Then there are some notes. I will upload them to the OULMS right after the day school. Then you can see my screen, I think. Then you can see about the wave functions. Then I want to memorize this. Then last day we discussed about the wave function. And we define about the probability of the wave functions, right? Then all the system, in the boundary system or whole system, we know probability of the wave function is equal to 1. Can you hear me?
Yes, ma'am.
Okay. Then wave functions totally, then summation of the wave function total value is equal to 1. We call this as the normalization condition. Then you can see we discussed this part in the last day. The probability of the finding the particle in state described by the wave function psi r comma t within the some volume dv about the point r x y z at time t, we can define p r comma t is equal psi rt dv, right? Then rt is position vector is r and t is the time vector. Psi is the complex conjugate of the wave function and psi rt is the wave functions, right? Then the complex conjugate is related to the in the complex numbers, then we can write minus value. And for the normal values, psi rt also for the psi star rt same as the psi rt. So psi rt squared is the probability. Then we can define this, right? Then other one is normalization conditions, right? Then for the normalization condition, we can find normalization constant, right? A normalization constant is and after the finding normalization condition, we can define our wave function well, right? Then the wave function we are defined within some constant, right? Then for the applying the normalization condition, we can find the normalization constant and we can define well uh, wave functions, right? I think you remember this. The probability of finding the particle somewhere in the entire space must be unity, right? Then we can integrate or we can take summation of the psi rt probability of the whole space. It should be equal 1 for all t values, right? For this condition, we can find normalization constant. If you remember. Then another one is we define about the expectation value, right? I took this expectation value as A. Then expectation value can define integration psi star complex conjugate and A and psi rt. Then sometimes it can be position, right? Position. Then position we define with the time and position. Then we can find the expectation value for the position, some limit, right? Not the entire system, some limit we can define by the integration. And other one, in the whole space, we can integrate our child star probability of the function. It means this is the normalization integer. So we know if the definition is this value, but this value is equal for the normalization integral of the wave function, it should be 1, right? Most of them answered the NBT2 in this part very well, right? I think people who are coming for the day school answer for the 2 questions papers well, right? Cannot hear me? One student spend the no sound. Can hear?
Can hear, madam.
Right? The normalization, right? Then these 3 parts are important for the introducing and finding some things in the Schrodinger equation. I will share blackboard. Right. This is the Schrodinger equation notes. I will upload this after the discussion. This part, I will upload this note to the Learn OS, right? Okay. Then I think you remember eigenvalue equations, right? In last day, in one of the last day, I discussed about the eigenvalue equation, and also you have the knowledge of the mathematical physics, and you remember the eigenvalue equation. So Schrodinger equation is the one of the eigenvalue equation, right? We are defined here time independent Schrodinger equation only, right? Then time dependent Schrodinger equation is also, but it's not in your book. And time dependent Schrodinger equation is for, can go to the further studies, right? To such a something, then at that equation, time independent one, time also varying, right? Very difficult to solve. It is for the higher mathematics and higher physics, right? If you are studying this Schrodinger equation well, then you can go to the higher mathematics values, right? Very interesting part, right? I think you also interested in this, right? Then Schrodinger equation is the experimental evidence suggests that the atomic particles were also wave-like nature. Then we know, then last days we discussed wave-like nature of the atomic particles, right? So the wave-like nature, we can define wave functions for the particles. So there should be a wave equation. If they have a wave-like nature, then we can define wave function. So there should be a wave equation to explain the behavior of the atomic particles, right? If not, we cannot explain it. Then we need to wave equation to explain the atomic particles, right? So then Schrodinger equation can do it. So then other thing is the Schrodinger equation is the eigenvalue equation. I think you remember eigenvalues. Then eigenvalue equations, I introduce some operators in your book. There are some operators, position, vector, and kinetic energy or something. And also you remember Hamiltonian. One of the operator is Hamiltonian, capital H in your book, right? And the eigenvalue equation, I explained it about some operators. Then Hamiltonian operator is the one operator, right? So then this is the Schrodinger equations equal to the in the eigenvalue equation. Then eigenvalue is equal to energy, right? The energy, we can define some energy levels in the quantum mechanical system, right? Then you can see this equation. H is the H hat. H hat is the Hamiltonian operator. Then we are applying the Hamiltonian operators to the wave function. H hat psi. It is equal E psi. So E is the energy. Then psi is same. So we can define this as the eigenvalue equation, and E is the eigenvalue, right? And we have to discuss about the three-dimensional, one-dimensional, and other things in the Schrodinger equation. Then Hamiltonian H we can define as the three-dimensional like this. Here you can see H cross square over 2, and we call this as the del operator, del square. I think you know del square plus VR. VR is the potential energy of the system, right? Potential energy can vary at the position. So VR is the potential energy, right? Hamiltonian confined with these two parts, minus h cross squared over 2m. You know about the h cross, h over 2 phi, and grad squared is, del squared is here, plus VR. VR defined as the potential energy. When we are doing the application, you can take more understand about the Schrodinger equation. And Hamiltonian is equal h cross square over 2m, and grad squared can define the partial derivations. If we are three-dimensional, del square is defined as W squared over W x squared plus W squared y over W squared plus W squared over W z squared plus VR, right? Then Schrodinger equation confined like this, minus h cross squared over 2m, and del squared can expand like this, psi r plus V psi r, it is equal E psi r. E is the energy of the system, and I is the eigenvalue of the system, right? I think you have some idea now. Then we can apply, this is to the some applications, right? then we can go more, we can get more idea about the Schrodinger equation, right? When we are then calculating, I am giving the equation. This is the Schrodinger equation. If not, then you can remember it, right? But I am giving, you can remember it because then you are going to study further studies. Then I think you know about the Schrodinger equation. It is not difficult. It is very easy one, right? Then gravity square, we can define like this about the 3 dimensions. If we are taking 1 dimension, 1D, like this in the x-axis, then d square by d square is a no need for the our calculation, and we can reduce this equation to minus s squared over 2n w square over w x square psi plus v psi r is equal e psi r, right? And I think you could get the idea about this, right? Then we can move to the application of Schrodinger equation. I will stop sharing it. We will see. They do the class in at the different place, right? Can you see clearly? Namai, can you see?
Yes, madam.
Okay. All right. Right. We discuss. Can you hear? If not, please tell me that. We discussed about the Schrodinger equation, and it is the eigenvalue equation also, right? H cross psi is equal E psi. Psi is the wave function. Can you see the board clearly? Clear or not? Clear?
Clear, madam. Yes. Clear.
Okay. H psi equal E psi. This is the Schrodinger equation, and H is the Hamiltonian. Then we are defined here wave-like nature of the particles, right? Then if we are considering wave function and we are you doing the calculation, we are apply Schrodinger equation for the some application, we need to know about conditions of the wave function. Then well-behaved wave function, some characteristics are here. Then we want to know about the wave, the characteristics of the wave function, because we have to apply some boundary condition for our calculation, right? Boundary conditions means sometimes we are doing applications. Wave function is going to one boundary to other one, right? One region to other region, like this. These are the two regions can happen, right? Region 1 and region 2. So, at that point, we need to know about the applying for the boundary condition. This is the boundary point. Boundary point here. Region 1 and 2, there is the boundary. Now we want to know what is the boundary conditions of the Schrodinger equations, right? And wave functions. What are the boundary conditions of the wave function? Then we have to apply the boundary conditions for this, right? Then we know, then we can define the wave function as the wave function must be finite, right? Must be finite. In page number 86, define the wave function's characteristic, right? Then for the boundary condition, we need to that. The wave functions must be finite, and the wave function and its derivation must be continuous, and the wave function must be single valued, should be a unique value at the given in physical point. Means the wave function, then here we can define wave function can vary because there is the boundary. Some can penetrate to this one, or some can reflect here. Then we can define psi 1 one wave part here, and other wave function can define psi 2 in the after the boundary. Then, but wave functions be finite that cannot be like this, right? And wave function is smoothly go into boundaries. So this is one value. And also we can take the derivations and the values of the wave function. It should be continuous. Continuous wave function. We are taking in this part d psi 1 derivation. dx, it should be equal d psi 2 over dx at the boundary. If boundary is, I am taking x as a, at the boundary point, the derivations and should be continuous. And also wave function should be continuous, right? Then this would be equal, right? There are boundaries. Then wave function should be smoothly well-defined wave function. It should be finite and it should be continuous wave functions, right? This one is cannot happen. So wave function should be like this. Okay. Then we want to know about these wave functions to apply for the Schrodinger equation for some applications, right? Now we can move for the applications of the Schrodinger equation, right? Then they are in laboratory, then sometimes an electrons, we consider single particle in motion, such as an electron, right? In the laboratory experiment, often involve beams of the particle. For example, a beam of electron from an accelerator fired at atoms in target, right? If the beam is not too intense, the interaction among the electrons are negligible and each electron interacts with an atom independently. Then we are considering here single particle in motion such as an electron. Then electron can move region 1 to region 2 like this. Then we are considering electrons, right? Then we have in 5 sessions. We have some application in the 5, including 5 sessions about the Schrodinger equation, right? We will see the first one, right? I think you have the basic idea. First one is session number 10. The potential step is the first application of the Schrodinger equation. It is the very easy one. I will explain everything in this, how we calculate, how we apply in the potential step. Then I can reduce some parts in the session 11 and 12, right? The first session, I will explain every and each things regarding the Schrodinger equation. Then next you can apply for the other parts, right? Okay, we will see. First one is the potential step. Session number 10. Application of the Schrodinger equation. Potential step. Please follow the step by step. It is very easy. I will tell some tips for the calculations. The potential step, right? In here, the potential step, we are some potential step. A particle moving particle, mass is m, sometimes it can be electron. They are given, we take the common particle, a moving particle of mass m is encountering a potential step, and we can define this, and we are thinking the particle is travel from left towards the potential step in the x direction. This is the one-dimensional example, right? With the fixed energy of E, right? This is the potential step undefined is Vx. Particle is going left, right to other part. Mass is m and moving is the x direction. Moving in the x direction, right? Mass m is encountering the potential step. Potential step is defined as 0 where x less than 0. Another one V naught where x greater than 0. And first thing is you have to draw potential step correctly. If not, the calculation is failed, right? Vx is equal 0, x less than 0, and Vx equal V naught, x greater than 0, right? They assume that the particles travels that where from left towards the potential step and the x direction with the fixed energy. We can discuss the fixed energy of the particle is E. We can take, sometimes they are giving the particle energy is less than V naught. Sometimes they are giving particle energy is greater than potential energy in the potential step. And sometimes they are giving particle energies greater than or less than or something. Then we have to discuss these two parts also, right? Then first thing I am taking, the particle is moving in the x direction with the fixed energy E, but E is less than V. This is your first discussion, right? The particle energy is less than V. Then first thing is you have to draw the diagram and you have to identify what are the regions the particle is passed in the potential step, right? Then you can see, then first one I am drawing, then next you can do V, x-axis. X-axis, only x-axis means it is the one-dimensional motion, right? Here, x-axis. What is the barrier here? What is the boundary? What is the value for the boundary? We define two regions. What are the two regions? You can see in this one. X less than 0 and x greater than 0. Right? Can you identify it? X less than 0 and x greater than 0. So boundary point is x equals 0. I think you can understand. Right? Boundary point is 0. And this side we can define x greater than 0 and this side define x less than 0. Okay? Then particle is coming. What is the potential energy? In this part, potential energy is 0. No any potential energy. We are drawing this axis, position and potential energy. Right? Position and potential energy. And the x less than 0, all potential value is, all potential step is less than 0 is 0. Then x greater than 0 side, it is equal to V naught. Right? Now we draw the diagram. Right? You can practice very easy. Right? In this graph represent our potential steps values. X less than 0, potential is 0, x greater than 0, potential is V naught. Then we can define the particle. Particle is coming to left towards and particle energy is capital E, but it is less than V naught. Right? If it is greater than V naught, it is going this far. Right? No anything can move. Right? But here is less than V naught. Particle is coming this side. M. You can draw like this, right? Then you can get idea. And if you are calculation, follow these steps, right? M is coming with energy E. E is less than V. Right? Now you can see particle is coming like this. Then what happened? There is a barrier. There is a step. So one thing we can do, it can be reflect. Right? It can be reflect. Okay? In the classical mechanics, we can, according to the classical mechanics, particle should be reflected at x equals 0 back to the x less than 0 region. Right? This is the classical mechanics. But in the quantum mechanically, we can define some particles in the other side also. X equal to. This part can be defined when some particles can be reflected and some particles are going after the barrier. Okay. Then you can see the particle can move how many regions? 2 regions particle should be passed for their for its motion in region 1 and region 2. The next step, first step is draw the diagram correctly and then mark the energy. Then it is less than or greater than. Then what is the path? Path is like this, right? When there is a barrier, then particle should be pass how many regions? 1, 2. There is 2 regions. There are 2 regions, first one and second. Then you have to mark these 2 regions. So wave functions are varying. Then psi 1 and psi 2 are not same, varying, because some can reflect and other can go to the other side. Then psi 1 and psi 2 different. But at the boundary, psi 1, psi 2 have some conditions. I explained them. They should be continuously passing the other side, but these are different because then the energy different. I think you understand. Then second step is mark the regions. Recognize how many regions here and then mark region 1 and region 2. Right? Now we can discuss about the Schrodinger equation, what happened in these 2 regions. Right? We will see. Then in region 1, we know kinetic energy of the particle because there is no any potential energy in this region. X less than 0, potential energy is equal 0. So in region 1, we know total energy of the particle is E. It's the kinetic energy of the particle. In where region X less than 0. X less than 0, kinetic energy of the particle is C, total energy is C, no any potential energy. E minus 0 is the total energy, it is equal E, kinetic energy of the particle, right? But in region 2, region 2 means X less than 0, there is some potential energy V naught. V naught is less than E, so we can write total energy E. Total energy is E, right? Total energy is E, and there is some potential energy. It is less value than E naught, so E minus V naught, right? What is this? This is kinetic energy of the particle. Kinetic energy of the particle, total energy is E. So E minus V naught is the kinetic energy of the particle, is greater value, right? Is greater the value. And minus V naught, we can define like this, right? Okay, then according to the classical mechanics, we are thinking about the classical mechanics, kinetic energy of the particle, E minus V naught, total energy minus V naught, this is should be less than 0. Negative value. It should be less than 0. E minus V naught, right? Because V naught is greater than E naught. So this should be negative value. Can you understand? Total energy of the particle is E. And there is going the region V naught. V naught is greater value. Then E minus V naught is the kinetic energy. V naught is greater than total energy. So this should be negative value. Okay. Then according to the classical mechanics, when we are thinking about the classical mechanics, kinetic energy of the particle is negative in region 2. So particle should be reflected at X equals 0 back to the X less than 0 region. Right? Then there is, according to the classical mechanics, not quantum mechanically, in the classical mechanics, there are no particles in region 2 because kinetic energy less than 0. We call region 2 is classically forbidden region. Right? We call this second region as the classically forbidden region. forbidden region, because in that region, in our calculations, kinetic energy should be 0. So it cannot be happened. Then we call, and totally, according to the classical mechanics, totally all particles should be reflected to region 1 at the boundary x equals 0. Right? We call this part as the classical forbidden region. Right? But quantum mechanically, we can define particles in region. Now we can apply Schrodinger equation to region 1 and 2. Then we can define psi 1 and psi 2, and we can go to the some calculations, expectations values, probabilities we can find, right? You have basic idea how to calculate probability, how to calculate expectation value. Now you can apply. We will see the calculation. Any problem up to now? Can you understand what is this potential step? Basic idea, I think you got the knowledge, right? I will tell some tips for the calculation. Please follow up them, right? Right. Again, I'm drawing this, our potential step at the x equals 0, our boundary. And this part x greater than 0, and other one x less than 0. Then this part is equal 0, and this one it is equal. V naught particle is coming within mass m with energy E is less than V naught, and we can define region 1 and region 2. It's when there are two wave functions, psi 1 and other one psi 2. Now we can find psi 1 and psi 2, right? Please follow the step I'm telling here. Right. At the region 1, first we are going to apply Schrodinger equation to region 1. Applying Schrodinger equation to region 1. To region 1, I am going to apply Schrodinger equation, right? What is the Schrodinger equation? This is the one-dimensional one, so we can write minus h cross squared over 2m d square over dx squared. I am defining psi x as psi 1x because I am in region 1 plus v psi x, it is equal e psi 1. I am taking psi 1, psi 1x. But in the region 1, we know the potential energy equals 0. Right? Potential energy is equal 0. So we can define again minus cos squared over 2m this part is 0, it is equal E psi 1x, right? E psi 1x, okay? Then I'm going to rearrange this equation like this. D square over dx squared psi 1x. I'm taking E to this side, then multiply by 2m, coming here minus plus 2me over h cross squared psi 1x, it is equal 0. Right? Then I'm rearranging this equation. Okay? Now, we can define one constant here. You can see 2me over h cross squared. It is the constant for the one particle. M is also constant for the particle. I am taking this one. Please follow the steps. As the constant, k squared as the squared value. Okay? take this constant as k squared. Can you see k squared? Then this is not the any difficulties because there is no v value. But if we are taking the constant, then other part I will explain what happened. When we are defining this constant, it should be positive value, right? K squared should be greater than 0. This is our tip. Then you remember this. If we are taking this constant, it should be greater than 0. It should be positive value. If not, we can take the solution, right? And this part also we have to arrange this constant as the positive value, right? It is the one tip, right? D squared over dx is squared plus 2me h cross is squared. We are defined this is as the k squared value. It should be a positive value, right? K squared equal 2me over h cross is squared. We are defining this constant as the positive value. Very, very important, right? It is serious in the sometimes there is the potential energy. It's complicated, but you should remember we are defining k squared should be positive value, right? Should be positive value. If not, we can define this, right? Then it is positive value. Now you can see positive sign here. Sometimes it can be negative, minus, but constant should be positive. Then this can be changing according to the potential energy. This sign can be changed, minus or plus, but you should define k squared as the positive because k squared now it should be positive. The square value should be positive, right? Now there are solutions. There are solutions. The solution of this equation we can define. If we are correctly define this sign and this, you can remember the solution of the equation. Solution can be defined psi 1x is the solution is equal a one constant e I k x plus b e minus I k x for the x less than 0, right? Can you understand? If there is coming negative value, minus sign and k squared is the positive value, the answer is changing. Answer is changing. Then you should remember this type of equation answer is like this. Right? One tip here, positive and 2me we are defined as k. The solution is exponential value with complex numbers ikx plus be minus ikx. Right? This type of equation. If there is negative value and this one is the positive, the answer is changing. So you have to remember what is the type of the solution. We can define positive and k squared solution is everywhere, not in the Schrodinger equation. For the squared values, mathematically the solution is like this, right? They should remember this sign and also this one. If there is positive, answer is like ae ikx plus be minus ikx, right? Ba and b are constant value. K is the wave vector, then k is here, 2me over h cross squared, then we can define, right? Then A and B are constants and we can be considered as the amplitude of the equations. Then we can find A and B after the applying boundary conditions, right? Then we call this equation as, you can see I value. This is in the region 1. There should be two wave equation. One is incident and other one is reflections. So positive value is the incident wave. We can take two parts. This is incident wave. Another one is minus. And there should be a reflection wave also because there is a boundary. So reflection. So we call this as the reflected wave. Right? Any problem? Please follow the step by step. Okay. Then A is positive value, we call this as the incident wave, and B value, we call this as the reflected wave. So there should be positive sign and positive k square. K square should be positive. Then we can rearrange the equation. K square take as the positive value. Then this sign can be negative, minus or plus, right? If there is the plus value, solution is like this. A e to the power ikx and plus b e to the power minus ik. There is the solution is the minus value. We will see what is the solution later, right? I think you understand. This is the first part equation. We can define for the region 1, and there are two waves, incident and reflections, right? Positive value incident wave we are defined as another one. It is the reflected value according to the quantum mechanical calculations, right? Okay, then A and B we can find after define the Chi2 also, we can find A and B also, right? Now, we call this as the incident and reflected plane waves in the region 1. A and B, we can define amplitude of the incident wave amplitude is A, reflected wave amplitude is B, right? Okay, now we will go to the defined region 2. Then after that, applying boundary condition, you can sort out the constant. I think you got the idea. Now we are moved to the region 2. Then region 2 is different. Then here coming minus. Then we can see what is the solution, right? Okay. Right. I'm applying Schrodinger equation to region 2. Right. This is our Schrodinger equation. Here, Chi2x, Chi2 and Chi2. Not like the region 1. In region 2, you can see some potential energy. V naught. V naught is greater than E, right? V naught is greater than E, so we can define this Chi2 plus V naught equal E Chi2. Now, we have to rearrange our equation. Want to take the 0 in this side after the equal sign. 0, then we can rearrange the equation. When we are rearranging the equation, you should remember the tip. Then we have to select the one constant as the positive. So this sign can be varied. I'm writing two equation. You tell me what is the correct one, okay? I'm rearranging the equation like this. Dx squared Chi2x, right? One is, I'm taking V naught and E, I'm taking this side and multiply by 2m and divide by h cross squared minus, minus, this is coming here, then positive way. One is, I'm taking 2m h cross squared, V naught minus E Chi2x equals 0. And I'm selecting positive sign here, but this one as the alpha square. Then alpha square should be greater than 0. This is my first equation. Okay. Then second equation, I'm rearranging this equation like this. Positive 2m over h cross squared E minus V naught Chi2x equals 0, and I am taking this one as alpha square. I want to define alpha squared as the positive value because it's square value. Then what is the correct equation? Equation A, OB. I can rearrange this type of, but I tell you, need to select the constant value as squared value and it should be positive. Then what is the correct equation? Rearrange equation. AOB. AOB. Can you hear me?
Yes, madam.
Vipula?
Correct. A වෙන්න ඕන අතර. මැද minus වෙන්න
It
ඕන.
should be correct. Yes, because V naught is greater than E. So we have to arrange the equation alpha squared as the constant greater than 0. So we should be take the correct equation as A. Right? Now you can see different equation here than the first one. Okay? Right. This is the correct equation. Because alpha squared is should be greater than 0. V naught is greater than E. V naught minus E greater than value. Now, sign is negative. Sign is minus. Right? Now, this is different the first equation. Right? Here, equation is d square over dx squared psi 2x minus alpha squared psi 2x equals 0. Now, solution can be written according to the mathematical. We can directly sign the equation. We do not need to solve the partial differential equation. We can take the direct solution, but should be, you can see minus value. In the previous equation, it was positive value. Now, equation solution is changing like this. Psi 2x equal CE minus alpha x plus DE alpha x. Then you can see no any complex values, no I values, right? Then you should remember what is the solutions of the two equations, right? There with some of them are teaching, not telling about this. These are the tips you can follow, right? Minus sign. The solution is like this. CE, not any complex numbers. Okay. Can you understand? CE minus alpha x and CE capital alpha x equals 0 because there is negative sign. And also we should select alpha squared or k squared. The squared value, no? Then as the positive. We have to rearrange the equation. Then you can directly take the solution. Then you have to remember what is the solution, like this solution, and there is the positive value, what is the solution. Then you should remember these two. Then you can rearrange all equations like this and you can answer the question, right? Now we can discuss the further. Then you can see in these are the exponential functions. E to the power minus alpha x. Another one is d e to the power alpha x. Then you can see what is the characteristics of this exponential function. Then we are taking CE alpha x. You can see this is the like this function. X and e to the power minus alpha x is the exponentially decaying function. And this value, positive value, it is exponentially growing functions, right? These are the behavior of these two functions. CE minus alpha x is the exponentially decaying function and DE alpha x is the exponentially growing function. Then in the x equals 0 is the one boundary. Psi 2x, after the boundary we are defined psi 2x. Then energy of the particle is now less because then one is reflected in region 1 incident wave and there is a reflected wave. Then after some small particles can go into the penetrate to the region 2. In the region 2, there are two different functions. One is exponentially growing, other one is exponentially decay. Some particle, then kinetic energy also less. Then can you understand what function can exist in this region? Exponentially decaying or exponentially growing function. There are two functions, but one can be in region 2. When we are considering properties of the particle, one should be here, other one is cannot exist in the region 2. Then can you think then there is a boundary. Then one is reflected and incident and reflected. Then also in the classically cannot be in the existing function in region 2. But we can define quantum mechanically. But then particles energy, when we are thinking particle energy, which function can be existing here? Decaying functions or growing functions? Anyone can be exist CE minus alpha x or DE plus alpha x. The behavior of the functions as CE minus alpha x is the exponentially decay. DE alpha x is exponentially growing. The particle is coming in the left-hand side of the region 1. There is a barrier, x equals 0, some are reflected. Small particles can penetrate in the region 2. Then how can we define that? How can we think about the energy of these wave functions? Anyone can tell? What is the can exist? Decaying or growing? Think and tell me. Vidula? Only one function exists in this region. Which one? CE minus alpha x is the decaying function. DE alpha x is the growing function. Which can be exist? Akshara, are you here? Akshara? Cannot explain? I told everything. Then you can define. What is the function? Exponent decaying one or growing one can exist. Can you hear me? Very interesting one. Then you can think. There is a barrier. Can hear me or cannot? මාව ඇහෙනවද? විදුල ඇහෙනවද මාව? Then what is the function you can define in this region too? There is only one function, one wave function. Other one should be 0. Other one should be not in the region 2. What is happening? Then what is the thing about the energy? Can grow in or can decay? Because then before that there was a boundary. What can you think about the energy of the part? Can increasing or decreasing? Akshara?
Region 1 again, madam, increase වෙනවා.
CE minus alpha x the DE alpha x the කියලා මම අහන්නේ. Make a decreasing function. You can see decreasing and growing in region 2. Right? Then I will explain. Then there is some wave functions. 2 can be exist in this region. One is incident, another one can be reflect. There is a boundary. තාපයක් කියලා හිතන්න. Boundary. Then හැපිලා එන්න පුළුවන්. Then other particles can go in the other side, small particles. Then what happened this energy? No any energy growing here. Energies then moving can decay. Decay, right? So CE minus alpha x can happen. The energy function here, energy is going to less than less value here. Decay function is decaying. In this function, energy is growing. But this cannot be exist because there is a barrier. පොඩි ප්‍රමාණයක් නෙන්නේ. ඒක energy එක වැඩි වෙන්න බෑ. එයා ටික මෙහාට move වෙනකොට energy is decay. Energy එක අඩු වෙනවා. So this one is not be consist in the region 2. Only this function is in the region 2, right? DE alpha x is the exponentially growing function. So DE alpha x cannot exist. Then we can define D goes to 0. D goes to 0, right? Now we can define 2 energy functions like this. Only 2 regions, regions 1 and region 2. We found energy functions. In region 1, what is the equation? We took psi 1x equal AEIKX plus BE minus IKX. We define this as the incident wave because positive value, right? This is the minus sign. It means reflected wave. This condition is coming particle energy is less than potential barrier energy. In region 2, psi 2x we can define energy is decaying in this part. So cannot exist energy growing function, only decaying function. So we can define psi 2x as CE minus alpha x. And here I am define k. K squared is equal to me over h cross squared. Another one, psi 2x can define, psi 2x here can define how CE minus alpha x, alpha is equal to m over h cross squared V naught minus E. If the potential barrier here, then sometimes then E can be greater than V naught. If there's just type of equation, then this is changing. And you can think, you know how to define a squared values and what are the solution according to these 6 values, right? Okay, now we have 3 constants, A, B and C, but we have only 2 equations, right? Then we have to find A, B and C, and that we applied boundary conditions, right? Initially, I told you about the boundary conditions. What are the characteristics of the wave functions behave in the boundary? So we can apply these boundaries conditions to find A, B and C. We will see. Applying, these are the steps you have to follow, right? Boundary conditions. Boundary conditions. The wave function must be finite. Wave function must be finite like this. Wave should be behave like this. These are the boundary. Or like this. Wave function should be finite. In the region 1 and region 2, then one condition we can take. I will draw in this, then you can understand better. Then x equals 0, these are must be finite. Then we can apply psi 1x should be equal psi 2x, where at this point x equals 0. This is the one boundary conditions, right? I am taking as psi 1x at the point x equals 0 should be equal psi 2x at the point x equals 0, right? Now we can apply 0 for this equation. In psi 1x, what happened? In the psi 1x, this equation, I am applying boundary condition. X equals 0. This is I0. E0 means 1. And E0 means 1. Then equation like this. A plus B. In other side also exponential function. X equals 0 means E0 is equal 1. A plus B equals 0. This is first equation. Now we are going to find A plus A and B and C. Okay. Understand? Then we are applying boundary condition. A plus B equals 0 after applying the boundary condition. Right? Now we can move to the second boundary condition. Second one. At the point x equals 0, we call the derivation should be equal. Other conditions of the wave function, derivation, first derivation, d over dx, psi 1x at the point x equals 0 should be equal d over dx psi 2x at the point x equal 0. Right? Then we can apply. What is our equation? Psi 1x equal ae pi kx plus be minus ikx. Now, derivations. Derivations, what happened? When we are derive this d psi 1x dx, it is equal a e to the power ikx into ik, right? Plus b here, minus, no? Minus b e to the power minus ikx into ik, like this, right? And other equation, CE1 d psi 2 over dx. And we are derivation, after the derivation, equation is CE minus alpha x into minus alpha, like this, right? Now we can apply boundary condition and x equals 0, it should be equal this one, characteristics of the wave function. Then we are applying 0. 0 means this should be 1, this should be 1. Then what happened? The equation AEIK minus B minus IK, no? Right, then we can write this equation as IK A minus B. It is equal minus alpha C. The second equation. After applying the boundary condition, this is the second equation. Then what is the first one? We take the first one. First equation is A plus B equals 0. C. A plus B equals 0. First equation. But there are only two equations, right? We applied all boundary conditions for the equation. One is psi 1x equals psi 2x. Other one is d psi 1x equal d psi 2x. This is there equal at the x equals 0 point. Two equations coming. 1 and 2 you can see. Only this equation can take applying the boundary condition. Then how we solve the equation? Only three constants, right? Only two equations. So we are assuming one is, we are knowing about the one, right? And then we can find other one using this constant, right? Normally we are assuming we know A is the non-constant. A is known. Then we can find using A, B and C, right? You can solve this equation B. After solving, you can see ik plus alpha over ik minus alpha into A. Right? මේ ඔය answer කරගන්න පුළුවන්. Ik plus alpha over A. Another one C is coming as 2ik over ik minus alpha. After solving the equation into A. Right? A again, අපි මේක හොයනවා. Right? A and B, now we are knowing about the equation. So we can write down our equations. One is psi 1x like this. Can define psi 1x is equal A eikx plus other one is ik minus alpha over, sorry, plus alpha. Ik minus alpha into A is coming out of the bracket, eikx plus E minus ik. So this is our wave equation in region 1. Right? A is non-constant. Right? A into eikx then can differ. Now, Then this is the incident wave part. AEI case is the incident part, right? And this is the reflection part. Now question is asking, then the question is coming, then find the Schrodinger equation, find the solution of the equation in region 1 and 2. This is the questions like this, right? Then asking, then you can define here incident and reflected wave. Then you know. Then question is asking, what is the position probability of incident wave? Now we can go back, right? We know how we define the position probability of the equation. To remember, I also remembered in the beginning of the lesson I told you, then probability can be defined chi star chi x, right? Chi star chi x. Then question is asking, what is the position probability of incident wave? Right. Then we can define position first wave equation like this, and question is asking what is the position probability of the part of the incident wave. Then you can define incident and reflection wave. AEI case, other one is reflected wave. Question is asking position probability of the incident wave. Right. We know what is the incident wave. Incident wave is AEIKX. We know position probability. PART, PXT. Here X no. PXT can define chi star X into chi X. Now you can see there is some complex numbers. This is the complex conjugate of the equations. So you can define Px comma T. What is the complex conjugate? Means here positive value. It should be my negative value in chi star, right? AE minus IKX into chi x define AEIKX. Okay, can you understand? Then we can define like this. Then position probabilities. What happened? IKX plus IKX come 1, A square. It is also amplitude is squared. Amplitude is squared, right? It is related to some intensities, right? We are not going further. Then we can define position probability of the incident wave as the A squared value, right? Okay. Can you understand? And also, then other one is reflected wave. What is the reflected wave? Then we can find position probability of reflected wave. Reflected wave. Same thing can do. What is the reflected wave? Reflected wave is IK plus alpha over IK minus alpha into A into E minus IKX. This is the reflected wave. Then position probability can define T is equal chi star and chi. Right? Then chi star, we can take the complex conjugate. Can take IK plus alpha and IK minus alpha 2 times here. No? Then A, these are the constant. Squared value, another one. Conjugate E plus IKX into I minus IKX. And this is coming. 1, the probability, position probabilities, answer is this one, right? A squared, right? I think you can understand. These are the steps we have to follow. Then if we sometimes can asking, draw some sketch about the region 1 and region 2, then you can see this is the simple application of the Schrodinger equation, right? Then you can see like this. These are the chi 1x, this side, and here chi 2x. Same reflection can see wave equation like this. We are thinking. and continuously moving, but in this side, exponentially decay function. We define exponentially growing function as like this, can decay in this side, right? In side 2x decay, not growing, then this should be d equals 0, right? These are the pattern of our wave equation. There is the reflection also. Reflection can be in this way. Same partner minus constant one and ikx minus ikx in other side. Okay. Very, very interesting one, right? Okay. Then we talk about E less than V. Now we can move in same application. Potential step E greater than 0. I'm not going to solve this part. I'm asking from you and you have idea. Okay. Right. We will see if particle energy is greater than V naught, what happened to our regions and what are the solutions, right? I'm not going to find all solutions, but I want to know if you understand or not, right? I want to know about this, right? You understand or not, right? Okay. We will move. E is greater than V naught. These are the potential steps. V naught in region 2 and x greater than 0 and x less than 0 this side. Here 0, x is equal. A particle is coming to left hand side, but V naught is greater than V naught, like this. E. And particle M is coming to this side. Now, then particle has to pass the two regions, region 1 and region 2. I want to know what are the solutions of the Schrodinger equation only. Then after steps you can follow as the same in the previous one. Want to talk about solution of the Schrodinger equation, right? Now we are going in the region 1. There is no any potential barrier. Only total energy and kinetic energy is same. E is the energy, right? Then I can define d square over dx square psi 1x in the region 1 plus not V value equal E side. We write the equation plus Vx, no, right? Minus h cross E squared over 2m. Schrodinger equation. V psi 1x. This is the total equation. E psi 1x, right? In the region 1, no any potential energy. Now we can rearrange the equation. Minus h squared over 2m, and you should remember constant is the square value. It should be greater than 0. Then we can take energy equation here. Minus h cross squared into m. I can multiply it. So equations become as plus, no, positive value. 2m is same as the previous. Plus 2me over h cross squared psi 1x equals 0. Right. This one is easy. We can define this equation. Positive, positive, everything is positive. As the k square, it is greater than 0. Now equation is d square over dx squared psi 1x plus k squared psi 2x equals 0. Then what is the solution? Then you can write directly. Right? Then you remember that. What is the solution? K square, same as the previous. Then we can write psi 1x is equal AEIKX plus BE minus IKX. So there should be, this is the incident, this is the reflected bar. Right? Okay. Can happen, can reflected. Then incident and reflected can happen. Now problem is with the region 2. We will move to the region 2. I'm going to minus h cross squared over 2m psi 2x plus v naught psi 2x equal e psi 2x. Now there is the potential barrier and condition is E greater than V naught. Then you have to rearrange the equation. How we rearrange the equation? Then sign is here, sign is positive or negative, it's okay. But we are define the square value of the constant. It should be greater than 0. Then you can rearrange the equation. Right? Try to rearrange the equation. Then we can write d square over dx squared. I'm writing like this. Psi 2x. Right? I'm writing like this. 2m over x cross squared into v naught minus e psi 2x equals 0. This is my first equation. And second one, d square over dx squared psi 2x plus 2m over x cross squared e minus v naught psi 2x equal 0. What is the correct equation? I want to take, without this sign, I want to take this as some constant. I'm taking as beta squared and O this value. Beta squared. It is the positive value. It should be positive because the square value. What is the correct equation? 1 or 2? Sign can be changed. Then this sign can be changed because 2 parts, no, one is 2 regions.
Second
What is the correct one?
one.
1 or 2? Huh?
2.
2. What is the correct one? Shaima? Rasin.
Second one.
Shaima Rasin. Second one, no? Oh, one answer in this here. Message. Hansi. No. Second one is the correct one. Vidula, are you there?
Yes, madam.
Okay. What is the correct equation? 1 or 2? First one or second? Vidula.
Okay, madam.
Second one is the correct one. Yes. Because then E is greater than V naught. So, correct equation is second one. And you can see here. Then we are defined in Hansi, second one, Hansi, right? We are defined in the previous part. We took E is less than V naught. And you can see here E is greater than V naught. The equation is different. So, second one is the correct. Okay. Because E is greater than V naught, then you can see then I sign. Right? Then if this sign is positive, previous value is negative, then solution is mathematically different, these two signs. I am writing two solutions. Tell me what is the correct one. Okay. Solution of the Schrodinger equation. I am writing positive value here and other one is this value. I am writing psi 2x equal C dash. I'm taking C dash because the previous one is e to the power I beta x plus d dash e to the power minus I beta x. One solution, right? One. Second one, I'm writing the solution. Psi 2x is equal C dash e beta x plus d dash e minus beta x. Can you see the board? Right? Then positive value here. Right? In the previous one, I explained what are the solutions. Can change positive and negative sign. Minus plus sign in the equation. Can change the equation. only these two solutions coming for the answers, right? Then you should remember mathematical expressions. That what is the correct answer for this solution? First one or second one? We know about these two equations. I explained in the previous.
First one, madam.
First one, right. Others answers, any different answers? First or second, then about the sign, then you can think sign. What is the correct answer? Second one or first one? Hansi, you are correct, right? Vidula, can you think? First one or second one?
Second one.
Positive sign. Vidula,
Greater than or
first
second
one. Then here positive, then if minus, then the equation is second one. So you should remember what are the answers here, right? Now E is greater than B not, then answer is take second first one. First one is the answer. Right. First one is the answer. She dash. Right. Then we can think about these two equations. Right? Then I value here. I values means one is incident and other one is reflection. I sign here. Complex numbers. In the mathematically, we can define the equation. Now, you can see in the region 2, this is the incident wave. This is represent the reflection. But in the region 2, you cannot see boundary or anything. The wave equation can go. But this is represent the reflection. So, we can see but in region 2, there is no any reflections, right? This is the reflection. So we can talk about this wave. In region 2, there is no any reflection, no any barrier, no any reflection. So we can take d dash should be equal 0, right? We can cancel one constant by discussing the properties of the functions in the boundaries. According to the properties of the boundary, we can take this constant as 0, no any reflections wave function because E is greater than V naught. There is no any boundaries in this region. So d dash is equal 0. Then we can take equation 2, region 2 as psi 2x equal c dash e to the power I beta x. Right? Now we know two wave equation in region 1 and 2. What's the first equation in region 1? We found psi 1x as the previous one, a e to the power I kx plus b e to the power I kx, right? And region 2, psi 2x can define, there is no any reflection, we can discuss like this, I beta x, only positive wave. This is the incident wave in the region 2, right? Then you can find A, B and C dash. How we find A, B and C dash? I'm not going to solve the A, B and C dash. We can apply boundary conditions. After solving the equation, we can apply boundary conditions. Right? What are the boundary conditions? Psi 1x. It should be infinite value at the x equals 0 should be equal psi 2x at the x equals 0. And also if the continuous functions, then d psi 1x over dx at the point x equals 0 should be equal d psi 2x over dx at the point x equals 0. And you can apply and you can take two equations and we can take A is the known value, then We can find B and C dash using the A value. Then we can answer the question, what are the probability of the reflection wave in the region 1? Then you can find psi star psi x. We know A, B and C dash. And can ask the question, what is the probability of the incident wave of the region 2? Then you can answer it, right? Very easy one. Okay. These are the applications of the Schrodinger equation. In the case, you can find the probabilities, incident, reflection, transmitted wave. This is called as the transmitted wave. Transmitted wave, right? In the region 2, no? We call this as a transmitted. This is incident. You know about this word because then question is asking incident wave. This is represent minus value, minus, right? Minus reflected. And in region 2, we call this as transmitted wave. Then question can ask what is the probability of the transmitted wave. Then you can answer. Okay. Right? Any questions regarding the potential state? Not, I can move the next round. Right? I am not going to explain deeply in other one. Now you know solutions of the Schrodinger equation. Only these two equations coming round by round, right? Okay. Right? Then session 11, second application of the Schrodinger equation. Second one is potential barrier. After the session, I will upload note, right? Second application of the Schrodinger equation is the potential barrier. In the questions, we are not give these words potential barrier. We are not in. We are define only the potential function. Then you can understand what is the potential barrier. Is this the potential barrier? Is this the potential step? Then you can understand, right? First thing is carefully drawing the wave functions. Carefully understand what is the potential energy, where the potential energy is zero, and you have to understand carefully. If not, initially, questions right? In the beginning, you are going to the wrong path. Then you have to understand how many regions here, right? It's the very, very important, right? We are considering one particle with mass m, simple m, with the total energy capital E, approaching from the left of the potential barrier. And potential barrier is defined like this. Vx is equal V naught, where 0 greater than equal x, greater than less than equal a. Another one, 0, where x less than 0 and a less than x. Can draw the diagram and can understand how many regions here? First thing is draw diagram and understand what are the regions. Then in steps we can discuss it. Then you can see x-axis only. It means one dimension. Still we are in one dimension. One is x equals 0. Here, other barrier you can see, other step you can see A, x equal A. I am taking this as A. This is the potential axis. This is the x-axis, right? Then x greater than 0 in this side, x less than 0 in this side. Right. Then V naught, where equal and A. Here also potential energy V naught. And here V naught. Right? In the other side, x less than A, potential is 0. This side is potential 0. And also x Ax greater than B, this side also potential is 0. Right? This is the diagram. We call this as the potential barrier. Right. The particle is coming in this side. Here also we can discuss about the particle energy. In the questions we are giving. Then particle energy is less than V naught or greater than equal, I mentioned, right? Then step 1. First step, I discuss about particle energy is less than V naught. Particle energy less than V naught. Then particle is coming in this side. Less than V naught means this side. E and N. Right. Anyone can tell me, then particle is going x less than 0 region to x greater than other side, left to this side. How many regions we can define? Previously we defined two regions, 1 and 2. How many regions the particle have to meet? Particle regions kiya combine. How many regions we can define? How many regions we can define in this session?
Madam, 3ක් පුළුවන්. 3 regions වෙනවා. Region 3ක් තියෙනවා නේද? 1 2 3.
Oh, 3 regions, right? Very good. 3 regions we have to define, right? Then 3 wave functions we have to define. Okay, we will see. First region, then නිකන් හිතන්න මෙහෙම ගමනක් යනවා කියලා හිතන්න particle එක. Then first region. ආයා බැරි එකේ මෙහා පැත්තට යන්න ඕන. 2 region second one. And තව බැරි එකක් තියෙනවා. Then quantum mechanically we can define the other side. Particle have to move past 3 regions, 1, 2, and 3. Then we can define 3 wave functions, right? 3 wave functions. Condition is E less than CV naught. Okay. Can you find the solution for region 1? One region 1 के solution එක විතරයි ලියන්නේ. Can you find the solution of the region 1? You have to apply Schrodinger equation in region 1 as the previous one. ඉස්සෙල්ල එක වගේම. You can find incident wave and reflections wave, 2 wave equation in region 1, right? We will try minus h cross c squared over 2m d square psi 1x over dx squared equal vx psi 1x equal e psi 1x. But in region 1, there is no any potential energy. Then this should be goes to 0. And you can find k value. I'm writing answer. Psi 1x is equal a to the power e I kx plus b e minus I kx, right? This is my first equation. This is the, what is the positive value we call incident, negative value we call reflected wave, right? And k square is equal to me over h cross squared. Okay, 1. Then we think about the region 2. What is the answer for the region 2? Right? This is easy. Now, region 2 is different. We will discuss about it. Region 2. Not different, then you can apply same equation, right? ඉඩමදිනේ. Right. In region 2, 1, 2, and 3. We are going to apply Schrodinger equation. Vx is equal V naught in the region 2. Then we can write d square psi 2x over dx squared minus, I'm clearing the equation like this, 2m over, then you try to write the equation, right? 2m over x cross c square, v naught minus e psi 2x equals 0. Or d square psi 2x over dx squared plus 2m over h cross squared e minus v naught into psi 2x equals 0. This is the equation 1 and this is the equation 2. Right. What is your solution? 1 or 2? Now, I'll have done anything. 1 or 2. I'm taking alpha squared or something. This is my alpha. In the equation 1, this is my alpha squared. In the equation 2, what is your solution? 1 or 2? They can time. Kadenne. Akshara ayudya, the akshara nedd. Hamdam innawaya. What is the equation? Mukadu oyala dene එක? Hansi? 1 or 2 is the solution of yours. Right, good. Others? Hansi is correct. Then Hansi can proceed the solution. Alpha squared can select two equation. What is the correct equation? 1 or 2? Very easy. Vidula වැඩ කරන ගමන් කොහෙද? 1. First equation is correct one. Yes. Because E is less than V naught, we want to take this value square value. So solution is first one. Then we can write solution of the equation and you remember minus sign here, alpha squared is which type of equation is coming? Psi 2x we can write taking some constant on f e to the power minus alpha x plus g e to the power plus alpha x or psi 2x f e to the power minus I alpha x plus g e to the power minus plus I alpha x. What is the solution for this equation? 1 or 2? Then we make alpha squared, that is b square psi x over minus constant squared. What is the mathematical solution? First one or second one? First one or second one solution? Previously I explained. Hansi? Yes, Hansi is correct. What is the solution? Vidula? කතා කරන්නේ යාළ විතර. First එකද second එකද? Akshara, are you there? Solution is the first one, right? First one is the solution because there is the negative value and alpha is squared. The solution is first one, right? Now, in region 2, a minus alpha exponentially decaying function and exponentially growing function, it can be happen in the region 2. Then there is two parts in the region 2, right? Then we can take two solutions also in the region 2, greater than equal x, less than equal a in region 2. Right. Now we can see region 3. Region 3 as the previous one, right? And you can practice this application. One of the application is coming for the final exam, right? Then psi 2x is equal like this. Then we can find the solution for the region 3, right? E is less than here, d square psi 3x over dx squared plus 2me over h cross squared. Why? There is no any potential in the region 3. In region 3, V is equal C. Only region 2 we can define V. In region 3, no any potential, then V is equal 0. Then we can define at the region 1. Region 1 විදිහටම define කරන්න පුළුවන්. 2me over h cross squared psi 3x is equal 0. Then what is the solution? Psi 3x is equal CEIKX plus DE minus IKX. K is equal to ME over h cross squared, K squared greater than 0. I'm taking same constant because in the region 1 also K 2ME over h cross squared, right? Then same K. Right? We can define like this. Then what is the, this is the incident one, this is the reflection one. So there is no any reflection. It is not possible in region 2, then the region 3, then D should be 0. Right? D should be 0. We can write, since no any reflections, of particles is possible.
Excuse me, madam.
Yes.
Why we took the exponential value for d minus ik?
Then a solution is coming like this now. It's the mathematical solution. We are directly taking the solution, mathematical solution. So this type of equation, solution is CEIKX plus DE minus IKX, right? But in the region 3, DE minus IX is represent the reflections wave. So there is no any reflections because there is no any barrier thing in the region 3. So we can take D is equal 0, right?
Oh,
Right, Shima?
okay.
Okay. Then we can take, since no reflection of the particle is possible, so we can write in region 3, D should be 0. D should be 0, right? Then we can write again equations, and then you can apply boundary conditions. There is so many boundary conditions. What are the boundary conditions? Then you can find A, B, C, and D constant. Boundary conditions can apply. What are the boundary conditions? We can take psi 1x equal psi 2x at x equals 0. Right? In this barrier. Then other one also can take psi 2x at the x equal a should be equal psi 3x at the x equal a. Right? And also we can take d value. If differentiate value psi 1x over dx at the x equals 0, it should be equal d psi 2x dx at the x equals 0. And same thing can write d psi 2x over dx x equal a equal d psi 3x dx at the x equal a. We have 4 boundary conditions. Then we can apply and can find constant in the equation A, B, C, D like this, and then define other reflection probability and things, right? Okay. These are the one application of the potential barrier, right? Then I will summarize things for the mathematical solution. Then one student asks, then we can write. Then you should remember like this: d square, shall you something by dx is squared minus alpha squared x is equal 0. This is the equation. Solution for this, we call this as the differential equation. Solution of this equation we can write directly. Directly we can write like this: y is equal ae alpha x plus be minus alpha x. Right? Another equation: d square y dx is squared plus k squared x. This is equal 0. This is the another type of differential equation. Directly we can apply. Right? Mathematical parts we can directly apply for the physics. So directly we can apply what is the solution? Y is equal ae minus ikx plus be plus ikx. Oh, positive value you can change. Positive value take this, right? And minus ikx. Only these two equations is help to calculations, right? Then you should remember. Very, very easy. And you have to rearrange the equation according to the energy value. Equal or positive value, right? Then we can identify the potential barrier also, potential step. Then you can find, right? Try day by day, then you can work out. Then then you should remember this. And when we are going to rearrange the equation, see carefully, because alpha squared, k squared are the positive values. Then you can change minus and plus value. And then go into the regions. Then you can discuss. Can happen reflection, can happen transmissions, right? Then think. Can exponentially growing, can exponentially decaying. You have to think. Then you can cancel some constants, right? If there is no any existence of the increasing function, then you can take the constant as 0 in the increasing part. Then decaying part, if you are thinking the decaying part is 0, then you can write it, right? Then you have to think, right? These are the basic idea of the Schrodinger equation, right? Rasin, now clear? Rasina or Rasin? Is it clear now?
Yes, madam. Yes, madam.
Okay. Okay, right. Now we can move to the other application. It is a little bit different than this value, right? We are going to define by using sine and cos, because we can define wave function, exciting wave energy levels. Very, very interesting part, right? Okay, we will see the next one. Also, we are in one-dimensional, the infinite square potential wave. Lesson number 12, right? Next applications. Uh, 12. When we are considering this one, the infinite well, we can move to the three-dimensional potential box. So carefully follow up this, right? The finite square potential well. Finite potential well. Here also we are considering a particle of mass m and total energy capital E. So I am defining potential energy Vx is 0, where in the region x less than a, another one infinite value, infinity value, then infinity elsewhere. The other, then potential cannot be found. It is infinite. Then potential is 0, again this region, right? Then we can draw a diagram. There are functions, right? Potential well. well එක. Right? Then we can draw the well. This is the x-axis. Right? One is, you can see two barriers, two boundaries, 0 and A. Right? In the 0 and A, between these 0 and A, what is the potential is 0. Potential is 0. In other side, they are infinite value. So I'm drawing like this, but this is goes to infinity. This is goes to infinity. Right? Linda, well, right? Infinite values in this side and this side. In the between this, we goes to 0. Right? Right. Then particle is coming in this side. We can see particle energy is greater than 0. Particle energy is greater than 0. Then particle is coming. Particle has to pass 1, 2, and 3 regions. 1, 2, and 3 regions, right? Then you can see there is 1 and 3 here, infinite potentials value. So we cannot define wave functions. Okay? This is goes to infinity. B goes to infinity. So we cannot define psi 1 and psi 3. Then we can write psi 1x equals 0 and psi 2x equals 0. Psi 3x equals 0. Then we can define wave function within this well. We cannot define these two because wave has to face the infinity value of the potential. Infinity value, right? Then we are defined only region 2. Can you understand? In region 2, there is the Vx potential energy is equal 0. Here, in region 2, potential energy is equal 0. Now, I'm going to show in the Schrodinger equation in region 2. There is no wave function. There is no wave function because it is in the finite potential values, right? In region 2, same as we can define what's happened. 0 less than x less than a. We know Vx is goes to 0. Vx equal 0, right? Now I'm applying Schrodinger equation. Psi 2x plus potential energy 0, 0 psi 2x equal E psi 2x, right? Now we can solve the equation. Again, as the previous one, you can see psi 2x we can define. I'm taking k squared is equal to me over h cross squared. So psi 2x is coming as a e to the power ikx plus e to the power minus ikx. Right? As the previous one. You can see equation 1. But for the calculation, we can define here in region 2 energy levels, energy wave functions one by one, step by step. Very interesting thing inside this well we can see. Right? In further discussion, further physics, very interesting solutions can see in this region potential well. Right? So, I am going to, then solution is like this. I am going to convert this into the trigonometric functions. Right? We can write this using sine and cos. Right? Sine and cos. Then I am writing this equation. In maths, students are knowing about. Then these exponential functions can change to the trigonometric part. Cos and sine we can replace this. Psi 2x I am defined. This is equal to a cos kx plus b sin kx. Right? We can go very interesting part if we are selecting trigonometric part than the exponential part. Right? Then in mathematically, a e to the power ikx plus b e to the power minus I kx can replace a cos kx plus b sin kx, right? Now I am taking second solution for our discussion, right? Okay, right. I will remove this. Our potential will here 0a only can define psi 2x. These are infinite number of value for the potential. So my solution taking as the trigonometric part, psi 2x is equal a cos kx plus b sin kx. Right. Now we are go through with this, go through the lesson with this equation, right? Right. A cos kx, sorry, x here plus b sin kx. Right. Okay, we will discuss. Now we can find a and b as the previous. We can apply boundary conditions, right? You can see two boundaries, x equals 0 and x equals a, right? First boundary condition, psi 2x. X equals 0 is equal 0. If this side 0, no, then psi 1x equals psi 2x is 0. Then we can write directly because this is 0. Psi 1x equals psi 2x and x equals 0. But psi 1x 0, we can directly apply psi 2x at the x equals 0 equals 0 and also other side. And the boundary psi 2x equals psi 3x at the point psi at the A. But at psi 3x is equal 0 at the point here, then we can write psi 2x equals 0, where the point x equal a. X equal a, right? Okay, then we can write psi x. Psi x is a cos a like this. And the point here, a into a cos k0. X equals 0. No? First boundary condition can apply. X equals 0 cos 0 plus b sin 0 equals 0. Right? Sin 0 is equal 0, but cos 0 is equal 1. So we can directly write a equals 0. A equals 0. One condition goes to 0. Right? At the first boundary condition, first equation is going at the 0. Then second one. In the second equation, second boundary. Right? Now a is 0. Then only b sin kx is remain. It's equal 0. Now we are going to apply a value, e value. Now we can write b sin ka is equal 0. Right? But in this equation, b cannot be 0. We want to fulfill this equation. B sin ka is equal 0. If b sin k is equal 0, what happens if b goes to 0 or sin ka should be goes to 0. If b is going to 0, then equation cannot define because already a is 0. If b is 0, what happens? Equation goes 0, not defined in our wave function. So, to fulfill this equation, b is not equal 0. If b is equal 0, no any wave function we cannot define. So, according to that, sin ka should be equal 0. Okay. This is not equal 0. Sin Ka should be equal 0. Then sin Ka should be equal 0 means Ka should be in N5. Multiplication of 5. No? Because sin 5 is equal 0. Then 5 to 5 like this, and we don't know what is the answer. Then Ka is equal N. N can be defined as 1, 2 like this. Ka should be N5. Then K is equal N5 by A. N5 by A. So we can define chi 2x, our wave function, as Bn. I'm taking as the Bn because there are so many wave equations we can define according to this integer. N equal 1 equation. N equal to another equation. So we are defined constant as Bn. Chi 2x I am defined Bn sin n phi over ax. N can be goes to 1 to 0 in other one, and x is defined here 0 x less than a. Now this is the solution. Any problem up to now? Anyone has any problem? Oh, clear. Applying boundary condition and define the wave function because A and B both cannot be 0 because if they are 0, we cannot define our wave function. So sin K should be 0. Then we can see K can be vary. A is the constant. N phi over A. K is the then sin theta like this. Sin theta equals 0 means theta is can the multiplication of phi. So theta is appear as the K should be multiplication of 5. Then K can define n phi over A. Now our equation is Bn sin n phi A over x. Okay, understand? Right? Now we have to find Bn. Anyone has idea how to find the Bn? Now we apply boundary condition. Then now wave function is confined with the 0 to A. Anyone has idea? Then before the Schrodinger equation, the experience of the cat 2, anyone can have the idea how to find the constant of the Bn. But what can we apply for what theory can apply? Wave function. Now there is the wave function. It is region is we can define 0 to A, and then within the well. And we found our equation Bn sin n phi over ax. Then we want to find Bn. Now there is the wave function. There is defined space here. Anyone has the idea how to find the Bn? කාට හරි idea එකක් තියෙනවද Bn හොයන්න? දැන් මේ ටික උගන්වලා තියෙන්නේ ඔක්කොම. එහෙමනම් ඔන්න හොඳ ළමයෙක්. හොඳට තේරුම් ගත්ත ළමයෙක්. How to find the Bn? Previous sessions වලින් අද උදේත් මම කිව්වා. කවුරු හරි කියන්නේ how to find the Bn? Which condition we can apply? Hasini, you have idea? Hansi, have idea how to find the Bn?
Normalization condition.
No, what is?
Normalization condition.
Normalization condition, yes. We can apply normalization conditions, right? Then in this region, probability, total probability of this wave function should be equal 1. Then if this condition, we can find Bn constant. Very good. Right. Then we can apply using normalization condition. What is the normalization condition? 0 to A, we are defined chi 2x star into chi 2x. This is the probability. In the entire space, it should be 1. It should be 1. Right? In our wave function, what's the wave function? Bn sin n phi x over A. Now we can write Bn is squared can take out of the bracket 0 to a sine n phi x over a squared dx. Now we can take sine 2a equation, cos 2a equation, then we can take bn squared. We can apply cos 2a equation. Please give 1 minute. Okay, sorry. It's going right. Bn is square. Then we can apply cos 2a equation, half into 0 to a 1 minus cos 2x. 2n phi x over a into dx. This should be equal 1. 1. Right? Then using this equation, we can calculate about the bn square. It's equal a by 2. In the first one, a by 2. And we can apply is minus sine 2n phi x over a. 0 to a is equal 1. Then what happens? This is goes to 0 because in apply a, sine value 0 and sine 0 also 0. This part is going to 0. Then Bn squared is coming as 2 by A, right? Yes, 2 by A. Then Bn, we can define 2 by A. Can see 2 by A squared. Bn constant can define as 2 by square value of 2 by A. Now we can define our equation Bn sin n phi x using the Bn constant. Psi nx, I am defining this as psi nx is equal to by A to sin n phi x over A. This is the one-dimensional part. In the next session, this is three-dimensional. In the x, y, z part, 3 times of x, y, z, right? And then if you are following this carefully, you can go to other one, right? 2a sin n phi x, we can define n is goes to 1, 2, 3 like this, right? And also, we define k squared. You remember, k squared is equal to me over h cross e squared. Also, k squared we can define. You remember, if we are taking b is not equal 0, sin ka is equal 0. In the previous, then ka equal n phi and a is equal n phi over a. Now, k square value is equal to me over h cross e square. We can write k square value n phi over a. Now, I am going to equal these two and find the value for the a, e, right? This is also equal n squared phi squared over a squared. Can you understand? K squared is defined this and k also equal n phi over a. Then we can equal these two. Then we can take the answer. Nice answer for E. You can see E can take n squared, phi squared, h cross e squared over 2ma squared. Right? N goes to 1, 2, 3 and like this. Okay? Nice answer. N here, I am taking this as EA. Now we have wave function. It is changing with N. And now we have energy values. It is also changing with N. Now we can define set of wave functions and also set of wave energy values. Energy values, right? If we are taking N equal 1, then what happens? Psi 1x can define wave function 2 over a squared sin phi x over a. And also n equal 1 means E1, energy 1, is equal phi squared h cross e squared over 2ma squared. Right? This is the smallest value of the energy. The smallest value of the energy because n equal 2, we can give another set of wave function, 2x. What happened? 2 over a sine 2, 4 phi squared, 2 phi x over a and E2 can define as how? Here n squared, I'm taking n equal 2. N equal 2 means 4 phi squared h cross e squared over 2ma squared. So, we can define set of wave functions with the set of energies. Can you understand? We call this as the smallest value. We call this energy as ground state energy. Then this is the n equal to, we call this as first excited state. First excited states of the energy. Right? Then like this n equal 3, second excited state. We can define set of energies and set of wave functions. Can you understand? I told you, that's why I am told you this is a very interesting question. Right? Then we can draw diagrams like this. Sign related, the equation is sine. First, n equal 1 is sin n phi x over a. I can define wave function like this. N equal 1. Second one can take like this within x equal a, right? X equals 0 to a. Only one right here. See a and 0. And also define n equal 3 like this way. Can vary like this, then make a line, alright? Then we can define, then also energy E1, ground state energy is E1. E2, we know that here phi squared over h cross h squared over 2m a squared. Then other one is 4 phi squared over h cross h squared over 2m a squared. It means 4 times of E1. We can write 4E1. And E3 also 9E1. Some question can ask, what are the energy changes goes to E3 to E1? What is the energy? Is E3 minus E1 is release. E2, it is equal 9E1 or minus 4E1. It can be 5E1. Or also question can ask, what is the photon? What is the wavelength of the photon? Then particle is goes to this one to this string. What is the energy of the photon? Then lambda of the photon or frequency of the photon. Then we can take this as h nu. Then you can find nu also. Very interesting questions can build up according to this, right? Can you understand? Right? Very, very interesting part, right? Only one dimensional square wave. Square wave. Okay. Okay. Then we know about the potential square value. Then we can move the infinite rectangular potential box, right? We can move rectangular potential box. It is also interesting. We know in the one-dimensional part, so very easy to apply this into the three-dimensional one, right? We will see. After the three-dimensional Y, I will stop the class. Then next day, both theory we can start, right? Because this is very complicated part, Schrodinger equation. Then you have to think and you have to practice, right? Okay, we are new to the infinite rectangular potential box. So it's square potential box. We can reduce it in the square one. Okay. Rectangle potential box. Right. We are considering particle in mass m confined to a move in a rectangular potential box. In the defined Vxyz, it is equal 0 in the region where 0 less than x less than a. This is the three-dimensional one because rectangular box, right? Another one 0 y b and 0 z c. Right? Then you can see the box like this. X, Y, Z we can define. Right? Then we can define Y-axis and Z-axis here and X-axis can take. Right? Then X is defined A. It means when we are taking one side, you can take it is equal to the square wave. Right? This side is equal A. In this side, we can imagine the square wave. Only one dimension. Another side is B. B is equal Y. The length of the Y is B. And Z value is equal Z. Length of the Z axis. And particle is confined within the box. Right? then you can see this is equal to square wave potential in the three sides, x, y, z. So we know how to solve the square wave potential. Then we can apply the rectangular box, right? Now, in the Schrodinger equation, you define is 0 within the box. So we can apply Schrodinger equation. H cross is squared over 2m. We are taking grad value. Grad square psi r defined. And V psi r is equal E psi r, three-dimensional part. Within the box, this is equal 0. Then we can cancel out this. Is equal 0. Then grad square can explain like this. Minus h cross is squared over 2m. And also psi r. Psi r can define equal psi xx, psi yy, and psi z, right? Psi r. Then can take the part by part. It is very easy. H cross is squared. What is the grad square? Grad square means da by squared over da by squared plus da by squared over da by y squared plus da by z squared over da by z squared. This is the grad square. Right now I am rearranging the equation according to this condition. Minus h cross is squared over 2m. I am taking da by square over da by x squared. I am taking x part in one side and other one here. Psi xx plus psi yy and psi z can take like this, right? And plus again can take da by squared over da by y squared psi y part. And other thing, psi xx and psi z. Okay, plus again da by squared over da by z squared psi z. Z part into others are psi xx and psi y. Okay. Then also we can write this is the h cross squared plus this is equal. What is the equation? Ex plus ey plus ez into psi x, psi y, psi z. Psi xx, psi yy, and psi z. We can rearrange the equation like this. Okay? Can you understand? Then we can take one-dimensional part by part. Then we can solve the equation. Okay? Right. I will clean the board because no space. And this is our equation. We can take by part to solve this equation. Right. I'm taking by x values minus h squares over 2m by differentiating this can arrange the equation 0 to a like this 2m d square over dx is psi xx in the x side plus 2me over h cross squared is x psi xx. This is equal 0 within this side. Right? This is as the previous equation in square wave potential. Same thing can do. I am taking this as equation A, applying the Schrodinger equation, this part, can solve this, and then can take part by part. Other one can take or 2m d square over dy squared psi yy plus 2mey over h cross squared psi yy. This is equal 0 where y and b. We can consider three equations as the square wave potential, right? And also with this equation can take part of the y z. d square over d square plus psi z plus 2mez over h cross squared psi z. This should be equal 0 where 0 to z to c. Can different take part like this, right? ඒ කියන්නේ අපිට මේ equation එක මේ equations තුනක් විදිහට කඩන්න පුළුවන්. පස්සේ combine කරන්න පුළුවන්. Right. Now we are know the solution. Solutions දන්නවනේ. In the part A, then square wave potential we take the solution and apply boundary condition. So we can directly sign psi xx. X equation as the previous discussion. I can write 2OA sin nx phi x over a. And also Ex is equal nx squared. I am defined nx squared. N as the nx squared, phi squared, h cross squared over 2ma squared like this. And also psi nx, ny, psi yy can define 2 over b. Because the side of the b, but if the y-axis is b, sin ny phi y over b. And also ey can define ny squared phi squared h cross squared over 2mb squared. At the previous session, we discussed the one-dimensional one. So I divided it by 3 equations. Then we can write the solution. Then after that, we can combine for the 3-dimensional, right? Then psi z equal 2 over c sin nz phi z over c. And ey z also can be written as nz squared phi squared h cross squared over 2me squared. These are the solution we can take in the part by part solve. But combined equation is like this. If you can take the one solution, then x පැත්තට තියෙන එක solve කරලා අරගෙන ඒ වගේ කියලා අනිත් ඒවා ලියන්න පුළුවන්. ප්‍රශ්නයක් නෑ. Combined equation can write psi nx, ny, nz, xy, z. Multiplication of that psi nx, psi ny, and psi nz. Right? Combined equation is equal 2 over කොහොම එළියට එනවනේ. එතකොට එතන 8. 8 over abc square root. Right? Sin nx phi x over a sin ny phi y over b and sin multiplication, right? nz phi z over c. This is the combined wave equation, right? And energy also can like this, right? Right? This is the rectangular potential box A, B, and C. If this is the cubical box, what happens? If cubical box, we can write A equal B equal C. So for the cubical box, what happened? This equation 8 over A3 into මේවා ඔක්කොම A කියලා වෙනස් වෙනවා. කියන්නේ sin nx x හැමමයි 5x over A sin ny 5y over A could be there. Sin nz 5z over A. Okay, we can reduce the equation like this, right? And energy levels also we can define. This is the cubical box. සමහරවිට cubical box එක ගණන් හදාන්න දෙනවා. Right? We are taking this as the equation number P. Now also energy levels. We will discuss about the energy levels. This is our equation for the cubical box. The cubical box, lambda is the cubical box. Then energy levels can define E, Nx, Ny, and Nz equal Nx plus. Energy එකතු වෙනවානේ. En by multiplication and make it plus En Z. Right? Then we can write total energy as 5 squared H cross C squared over 2M. And Nx squared is plus Ny squared B squared. This is rectangular box, right? And Nz is squared since it can be Nx, Ny, Nz ඔක්කොම යනවා. Nx, Ny and Nz goes to 1, 2, 3 like this, right? Combination of the square well, then 3-dimensional one, then 1-dimensional one එක එකතුවක් විදිහට එන්නේ, right? Also we can define if this is the cubical one. If cubical box, what happened? A, B, C ඔක්කොම සමාන 8. For the cubical box, we can define total energy Enx, Ny and Nz is equal 5 squared H cross C squared over 2M into A squared. No, A squared can take the out of the bracket. It is equal Nx squared Ny squared plus Nz is right? Can define like this. And also we can define the wave functions. Then this is our wave equation for the cubical box. And for the energy values is cubical box. Then Nx, Ny, Nz can change. ඒ හතුනම වෙනස් වෙන්න. එහෙනම් මොකද වෙන්නේ? We can define first excited state. එතකොට කලින් ගත්ත ඒ වගේ තුනක් නෙමෙයි. Can define how? ඒකේ first excited state එකේ Nx equal 1, Ny equal 1 and also Nz equal 2. ඒක define කරන්න පුළුවන් 1 1 1 wave equation එක ගත්තාම, right? Lowest energy, sorry, equal 1, sorry. Nz equal 1. Lowest energy. The lowest energy, sorry, ground state. First one is ground state. Ground state can define all integers are equal 1, right? E1, 1, 1 is equal 5 squared, H cross C squared over 2Ma squared. This is for the cubical one. 1 is squared plus 1 is squared plus 1 is right? This is equal 3, 5 squared, H cross C squared over 2Ma squared and also psi 1, 1, 1 XYZ can define 8 over A3 sine 5x over A sine 5y over B and sine 5z over A. Sorry, A. We are taking cubical box. And then we can define E1. But we are going to the first excited state. First excited one, it can be changed. How? Nx, Ny equal 1 and Nz can 2. එකක් 2 වෙන්න පුළුවන් අනිත් ඒවා එකේ right? And also Nx, Nz equal 1 and Ny can 3, 2. Other one, Ny, Nz equal 1. Nx can be the first excited state n squared equals 6, right? N squared equals 6. Then you can define energy values E11, Chi11 also, right? Then we can see some excited in the first excited level, the number of different status that corresponding to the one energy level. Energy is equal, same energy. For the first excited state, these are the condition for the first excited state. So, energy is same. E112 equal E121 equal E21. This is equal 6, 5 squared, H cross C squared over 2Ma squared. But we can see energy functions 1, 1, 2. Psi 1, 2, 1. Psi 2, 1, 1. You can see different wave functions, right? This is equal 8 over A3 squared sine 5x over A, 5y over B, A and sine 2, 5 is a over A. This is different. And also other one, 1, 1 also changing. Here coming sign 2, 5 y over A. Others are same. And 2, 1, 1 also sign 2, 5x over A. Others are same. Then you can see one energy define 3 wave functions. We call this as the degeneracy. We call this as the degeneracy because only one wave function, the number of different states that corresponding to the one energy. Right? Number of different states, but that corresponding to the one energy. Okay? We call this as the degeneracy. Right? I mean the one-dimensional one can expand to three-dimensional one. So have knowledge of the one-dimensional. I will share note with the wave functions here. I will upload this, right? You can see three-dimensional one. Yes, here rectangular box. Boundary conditions apply. Then you can define for the cubical box A equal B equal C and energy levels can differ, right? Here. Right. Then ground state energy E1 1 and define one wave function. But first exercise digit you can see E is energy is equal value. For the all energy only one value. But we can define three wave functions. Here 1 1 2 1 2 1 2 1 1 can define three wave functions, right? Then we call degeneracy. What is the degeneracy? D exists in the first excited state. You can see the degeneracy, but the number of different states, here 3 states, but corresponding to the one energy level, right? We call this as the degeneracy. Can you understand? This is called as the degeneracy. Please follow the square wave one very well. Then you can move to rectangular potential well because there is some. I'm considering 3 parts and you can see, right? Equation 1 and second equation can solve EX like this, and I'm taking X part here in equation A, Y parts in equation B, and C equation Z is in equation C. Then apply boundary condition, other things we goes to this equation. It is also just like the one-dimensional square well in X side, Y side and Z side. Then combination of these three we can take as the cubical box or rectangular box. If there is the cubical box, A, B, C is equal 1 well, right? I think you got the idea. This is the end of the Schrodinger equation, application of the Schrodinger equation. Then we have to discuss about the Bohr theory and hydrogen atom. I think then contents is heavy. I have some notes regarding the Bohr theory also. Right. I think better to discuss in the next another day. I am planning to do 12, morning or evening. Evening is better time, but the heavy rain sometimes appear.